For the last module for this chapter, we're going to cover a couple different things. So first, we want to use Hess's Law. We're going to use Hess's Law to determine the enthalpy change for a reaction. Hess's Law comes back the rest of your time in chemistry, especially Gen Chem. So when you learn Hess's Law, it's not a difficult concept once you get it, but it can be difficult for students initially. So please spend time understanding and learning Hess's Law. We also are going to work on writing standard formation reactions for any compound. You must know the most stable form of common elements. Know the substances which have a standard enthalpy of formation of 0. Remember, standard enthalpy of formation is a molar quantity. Use standard enthalpies of formation to calculate the delta H for a reaction, and use standard molar enthalpies of formation to determine the standard molar enthalpy of combustion of a compound, and vice versa. So first, Hess's Law. Hess's Law is a game changer. It's a very useful tool that we use all the time in chemistry. I use it even when we're not in thermodynamic chapters. It's an important thing for you to understand. Hess's Law itself states, the total enthalpy change, delta H, for a process is the same, regardless of whether the reaction occurs in one step or many steps. And this does not have to be specific to enthalpy. We're using an enthalpy in this chapter, but it does not have to be specific to enthalpy. We can do this when we're looking at other types of concepts as well, and we'll see that as you continue on in chemistry. For today, though, I want you to see the total enthalpy change for a process is the same regardless of whether the reaction occurs in one step or many steps. So that's what's showing over here. If we look at the two pictures here, we see increase in enthalpy here, okay? Here, let's say we do this reaction in parts. One part here, delta H1, one part here, delta H2. Overall, your entire enthalpy change is still this whole distance. So we could do this as one swoop or parts, but overall your change in enthalpy, the entire change in energy of this reaction, is going to remain constant. Same thing here, if we have an initial state and a final state, if we go through intermediate A or intermediate B, it doesn't matter. We're still going from the from initial state to final state. It doesn't matter how I got there, it just matters that I'm there. I'm going to use Hess's Law in different reactions and manipulate them to get to my desired reaction, and then I can determine the overall delta H for that reaction using Hess's Law. If a reaction is reversed, the sign of delta H is also reversed. So if it was positive, it becomes negative. If it was negative, it becomes positive. The magnitude of delta H is directly proportional to the quantities of reactants and products in a reaction. If the coefficients in a balanced reaction are multiplied by a number, the value of delta H has to be multiplied by that number as well. Remember, we told you delta H is specific to the number, the coefficients for the products and reactants we have. We saw in the example with the N2O2 going to NO that when I divided through the reaction by 2, I also divided delta H by 2. So let's go ahead and apply Hess's Law. Example problem. Use Hess's Law to calculate delta H for this reaction. So this is what I call your target reaction. It's our targets, it's what we're trying to find delta H of. These are your given reactions. I want you to manipulate these equations such that we're going to obtain your desired reaction. How can we do that? Well, what I want you to do is compare each of your given reactions to your target reaction and see where the overlap lays. I've got 1 mole of CO here. I've got 1 mole of CO here. I've got O2 here. I don't have any O2 up there. I have CO2 here and I have CO2 here. What this tells me, I've got CO and CO2. Those are common to my target reaction, but they're on the wrong side. This has CO on my reactant side, this is on my product. This has CO2 on my product side, this is on the reactant. I'm going to flip this equation around. When I flip this equation around, I just realized I keep forgetting to write down the delta H values on this actual slide. So let me write them right here. Delta H of this one It's in the student notes, but I forget to write it on the slide. Negative 283 kilojoules. Delta H for the second reaction, positive 571.6 kilojoules. And delta H for the third reaction, negative 44.0 kilojoules. Okay. But I'm going to flip this reaction. When I flip this reaction, that means I also flip the sign on delta H. So let's go ahead and rewrite that. CO2 gas is now my reactant. CO is now a product. And 1/2 O2 is also a product. Because I flipped it, I'm going to flip the sign on delta H. Delta H now becomes positive 283 kilojoules. Let's look at our next one. Got water. I don't have any water in my numerator or my target reaction. H2, or I lied. I've got water and I've got water here. H2, H2. O2 is what I was thinking about. O2 is not in my target reaction at all, and it is here. So I'm just going to ignore O2 for right now. But I do also notice that my water is on the wrong side and my H2 is on the wrong side. So I need to flip this reaction. But also note that I have 2 moles of water here and 2 moles of H2 here, whereas I have 1 and 1. So not only do I need to flip, I need to divide this reaction by 2 or multiply through by 1/2, whichever way you want to see it. Now I have H2 gas plus 1/2 O2 gas, giving me 1 mole of H2O liquid. And delta H here is going to be a negative 571.6 kilojoules divided by 2. I didn't actually calculate that out. I just wrote it out as divided by 2. You can calculate it out if you'd like. I will do that in a sec. The last reaction we have here, H2O going to H2O gas going to H2O liquid. Now, note, I had H2O here, and I said, oh, look, I have H2O. What I didn't pay attention to, let me erase some of this, I've got writing everywhere. What I didn't pay attention to is this is a liquid. This is a gas. I need gas. So this is actually useless to me. I still needed to half it because I needed I needed 1 mole of H2. But I got H2 liquid here. I got H2 gas here. This is the one I need on my product side. This is going to be used to cancel things out in just a sec. So let's go ahead. This reaction also needs to be flipped because this is gas, and I need the gas on my product side. So this will be flipped as well. That gives me H2O liquid. Going to H2O gas. And my delta H value becomes positive 44.0 kilojoules. Because I have successfully run out of room. 1 second. Okay, what I want you to do now is I want you to add up these equations. But when you do that, when you add these up, I want you to look for commonalities and see if there's anything on the reactant side and product side that can cancel out. I've got CO2, and I don't have CO2 anywhere else. So I know I've got 1 mole of CO2 gas. That also matches here, so we're good there. That's all my reactants in the first equation, so I'm going to move on to the second equation. I've got 1 mole of H2, and I don't have H2 anywhere else. So I'm also going to write that down. That also matches. I have a 1/2 mole of O2 here, but I have a 1/2 mole of O2 here as well on the product side. So those will cancel each other out. It's kind of like how we cancel out spectators in the solutions chemistry chapter. I've got a 1/2 mole of O2 on my reactant side, 1/2 mole on my product side. Those cancel each other out. I then have 1 mole of H2O liquid and 1 mole of H2O liquid. Those also cancel out. That's all my reactants, and it's all my reactants, so I'm good so far. Go on to products. I have 1 mole of CO gas and 1 mole of H2O gas. And that matches. I have successfully obtained my target reaction. Now what I'm going to do is I'm going to plug this into my calculator. I'm going to say 283.0 minus 571.6 divided by 2 plus 44. And I'm going to get a delta H value of 41.2 kilojoules. This is the answer for this equation. All that work for this little answer. But that is your delta H using Hess's law. So Hess's law allows us to basically manipulate other equations to get to our target equation. You absolutely must be able to do this. It's important in this chapter and throughout the rest of your chemistry time. You will see this pop up when you don't expect it. It's very important you can manipulate these equations. Let's talk about enthalpies of formation. A formation reaction is a very specific definitional type of reaction. We do say delta H naught of sub F, F meaning formation. A formation reaction is defined as forming 1 mole of a substance from its elements in their most stable form. Delta HF is the shorthand for particular, is the symbol we use, and it is a shorthand for a particular thermochemical equation. So standard enthalpy of formation, delta H sub F, delta H naught. We do say the word naught for that little symbol, and it's the enthalpy change that occurs when 1 mole of a substance is formed from its elements in their most stable form. I know I've said that more than once, but it's very important that you understand that you are forming 1 mole. So product side equals 1 mole of something. Because of that, we can actually have fractions as coefficients. It's the only time you can have fractions as coefficients. Example, for carbon monoxide, delta H of formation is equal to negative 110.5 kilojoules per mole. Write the corresponding thermochemical equation. I am trying to form 1 mole of CO gas. I know delta H of formation is equal to negative 110.5 English is hard today, kilojoules per mole. I need to form that from the elements in their most stable form. I've got carbon, I've got oxygen. Carbon, how do you know this? You just have to memorize carbon. Carbon's most stable form is graphite. So it'll be carbon, graphite. 1 carbon, 1 carbon. Oxygen is a diatomic and gas phase. I need 1 oxygen here. I need to balance this equation. I'm going to say 1/2 O2. Fractions are allowed. Only in thermochemical equations, though. Do not do it outside of this, okay? The key to this is that sometimes fractional coefficients are required. Sometimes we just can't get away with it, or away from it, because by definition, we have to form 1 mole. So again, sometimes fractional coefficients are absolutely required. Let's look at KClO3. So, what do you guys call this? Hopefully you guys know the name, potassium chlorate. Delta H formation is equal to negative 397.73 kilojoules per mole. Write the corresponding thermochemical equation. So I'm forming KClO3 solid. Delta H formation is equal to negative 397.73 kilojoules per mole. per mole, 1 mole. What goes into here? Potassium. Potassium is a metal. It is a solid. The only metal that's not a solid is mercury. I've got chlorine, Cl2. Chlorine is a gas. Bromine's a liquid, iodine's a solid, but chlorine is a gas. I need 1 of them, so I'm going to say 1/2. I've got oxygen. Oxygen also a gas. I need 3 of them, so I'm going to say 3/2 O2. And that will balance out to give me 1 mole of KClO3. So there are some substances that always have 0 as their standard enthalpy of formation. These substances are any neutral element, meaning not an ion, in its most stable form. Why? Well, let's think about this. I've got O2 gas, forming O2 gas. My delta H formation is 0 because nothing happened. It didn't have to be formed. It was just that way naturally. Okay, Hess's Law. As a consequence of Hess's Law, we can use delta H formation values to calculate delta H of an overall reaction. These values are in your textbook. They're in the appendix of your textbook. I call this your products minus reactants equation. That's not incredible. That's not technically completely correct, but if you can remember products minus reactants, your brain will probably get you back to the right point and you'll get it right. You'll be able to do these calculations hopefully more successfully. The better definition here is this reaction. Delta H reaction is equal to the sum of the number of moles of product times the delta H formation for that specific product, summing all of that together, minus the sum of the number of mole of reactant times the delta H formation for that specific reactant, and sum all the reactants together. N and P represent the stoichiometric coefficients for each product and reactant. And if you remember products minus reactants, you should probably get to the right point. But let's go ahead and work a couple examples just so you can see what I mean. Use the following standard enthalpies of formation to calculate the standard molar enthalpy of combustion of glucose. First, you got to remember what combustion is. Hopefully you guys have this down by now. Glucose C6H12O6. To combust means it reacts with O2 to form CO2 and water. You do have to balance this out. So balance out our carbons, 6 carbons, balance out our oxygen, and now we need to balance out, let's see, we've got 6 times, my brain is tired. 6 carbon, 6 carbon, 12 hydrogen, 12 hydrogen. So what is that? 12, 18 oxygen. So put a 9 in front of here for our oxygen. 9 oxygens. Oops. We've got your values here. So we're going to use these to figure out the delta H of reaction for this entire reaction. So how are we going to do this? Delta H naught of reaction. We're going to think products minus reactants. So products first. We have 6 moles of CO2 times the value for CO2. Negative 393.5 is your delta H formation for CO2. That is kilojoules per mole. Plus 6 moles of water times the value for water, negative 285.8 kilojoules per mole. Note that this is for water liquid. This is for CO2 gas. They are different depending on their states. That is all of my products. Now I'm going to subtract my reactants. I've got 1 mole C6H12O6 times negative 1260 kilojoules per mole plus 9 moles O2, and there's no value listed because it's O2, it's 0. This cancels out my moles, gives me kilojoules. And when you add this all up, let's put delta H reaction here. So this is for CO2, this is for H2O, this is for C6H12O6, and this is for O2, just so it's labeled for you guys. Delta H reaction, negative 2815.8 kilojoules, which gives me negative 2816 kilojoules. 2,816 kilojoules is the standard molar enthalpy of combustion of glucose. So I've used the delta H formation to figure out the overall reaction. This isn't hard for most students, but you've got to remember products minus reactants, and when you're working these problems yourselves, you've got to remember to pick the right state. Oftentimes we'll just give you a table with values, and you guys have to pick the right state. And that'll be based on your balanced reaction. Okay, let's work another example. Chromium metal that's used in chrome steel is obtained by heating the ore chromite, FeCr2O4, with carbon. Let me see that listed here. The reaction is given, and it gives my delta H value of positive 988.4 kilojoules. Given that the standard enthalpy of formation of carbon monoxide is 110.5 kilojoules per mole, calculate the standard enthalpy of formation of FeCr2O4. Well, I know that my delta H for my reaction is equal to products minus reactants, so I know this is equal to delta H formation of iron. I've got 1 mole here, plus 2 moles times the delta H formation of chromium, plus 4 moles times the delta H formation of CO2 gas. And that's all my products minus my reactants. 1 mole times delta H formation of chromite, FeCr2O4, and 4 moles delta H formation of carbon, graphite specifically. Shrink this down so I can fit it. So let's plug in everything we know. And we're trying to find what is this value. We're trying to find, what are we trying to find? We're trying to find formation of Fe2CrO4. So we're trying to find this. I know this value because it was given in the problem right here. So positive 988.4 kilojoules. So I know that 988.4 kilojoules equals 1 mole times 0 kilojoules per mole for Fe, most stable state, plus 2 moles, 0 kilojoules per mole for chromium, most stable state. Four moles CO2 tells me CO2's value, negative 110.5 kilojoules per mole. It's all my reactants, or all my products. Look at reactants. I've got 1 mole times what I'm trying to find, delta H formation of FeCr2O4, and 4 moles, 0 kilojoules per mole for carbon graphite, most stable form. Solve all that out, and you should get delta H formation of FeCr2O4 to be equal to negative 1,430.4 kilojoules, which simplifies to negative 1,430 kilojoules per mole for sig fix. So you can use this equation to determine values as well, if you know the overall reaction. Let's work 2 more example problems that are a little more complex and kind of tie the chapter together, and then the additional practice is there as well. In a coffee cup calorimeter, 1.5 grams of nickel chloride is mixed with 50 grams of water at an initial temperature at 25 degrees C. After dissolution of the salt, the final temperature of the calorimeter contents is 24.25 degrees C. Assuming the solution has a heat capacity of 4.18 joules per gram degree C, and assuming no heat loss to the calorimeter, calculate the enthalpy change for the dissolution of nickel chloride in units of kilojoules per mole. Okay, so lots going on here. We've got 1.50 grams of nickel and 50 grams of water. That means in total, I have 51.5 grams of your system, which is the solution, the aqueous solution itself. Let's say the first law in words, the first law of thermodynamics, just to kind of wrap our brains around what's going to happen in this example. The heat lost by the surroundings is gained by the system. How do I know that heat was lost by surroundings and gained by system? Because the temperature decreased. The temperature of what I was monitoring decreased. I can monitor the solution. The solution contains the little particles. I'm monitoring the solution, which is acting like your surroundings. The temperature decreased, so the reaction is endothermic. So we think about the system as being at 51.5 grams, but really that system is a solution. The solution contains your system and your surroundings. This is endothermic. It takes heat to dissolve your nickel chloride. So my surroundings lost heat. My system gained heat. I can find Q of my surroundings because, again, this whole thing, what I call the system here, is actually my solution. That's actually my surroundings. It contains the nickel chloride and it contains the water. We're measuring the temperature of the water itself. The reaction, those particles, that's your system. Everything else, your solution, is your surroundings. So Q of surroundings, because that's what I'm actually measuring, is your MCAT equation. your mass, we do have 51.5 grams here. I've got the 1.5 grams of your nickel chloride and the 50 grams of water. 51.5 grams times specific heat of water. Again, you need to know this number, 4.184 joules per gram degree C. And our change in temperature. Our final temperature is 24.25 degrees C. Our initial temperature is 25 degrees C. Because the temperature decreased, I know it's an endothermic reaction. The change in temperature here is negative 0.75 degrees C. This gives me negative 160 joules. So again, units are canceling here, giving me my joules. I want this in kilojoules per mole. Right now I have joules. Getting to kilojoules is easy. That's like saying negative 0.16 kilojoules. Okay, that part's the easy part. But I need the moles. Moles of what? Moles of nickel chloride. .50 grams of nickel chloride times 1 mole of nickel chloride. Molar mass of nickel chloride, 129.6 grams. 0.0116 moles of nickel chloride. Now, my Q of my system. I know my Q of my system is opposite of my surroundings, and this is surroundings because I can measure my solution, which is my surroundings. Positive 0.16 kilojoules divided by 0.0116 moles gives me 14 kilojoules per mole. So the enthalpy change for the dissolution of nickel chloride in units of kilojoules per mole is 14 kilojoules per mole. I have one more example here before you guys finish before the chapter's finished, and if you can look at the additional practice problems for additional help. But let's look at this one. We have a coffee cup calorimeter again, where we mix 50 mils of a 0.1 molar silver nitrate solution and 50 mils of a 0.1 molar HCl solution. The two solutions were initially at 22.6 degrees C. The final temperature is 23.4 degrees C. Calculate the heat that accompanies this reaction in kilojoules per mole of silver chloride formed. Assume that the combined solution has a mass of 100 grams and a specific heat of 4.18 joules per gram degree C. What is delta H of this reaction? This is our net ionic. So it's showing us just what's involved in the reaction. So I've got silver nitrate. I react it with hydrochloric acid. I produce silver chloride and nitric acid. I have 50 mils in a 0.1 molar solution of both silver nitrate and HCl. Remember that molarity is number of moles divided by liters of solution. So to find number of moles, I can take the molarity and multiply it by the liters of solution. So number of moles, silver nitrate, 0.100 moles per liter, times 0.0500 liters. That's converting this to liters. Gives me 0.00500 moles silver nitrate, which also gives me 0.00500 moles of silver ions because it's a 1-to-1 relationship. Do the same thing with HCl. Number of moles of HCl, 0.110 moles per liter times 0.0500 liters gives me 0.00500 moles HCl, which also means 0.00500 moles of chloride ions because it's 1:1. Now let's do the first law in words. The heat lost by the reaction must equal the heat gained by the solution. How do I know that heat was lost by the reaction and gained by the solution? Well, let's think about what's going on here. We've got a styrofoam coffee cup. So it's basically two coffee cups nestled one in front of, or one inside the other to help keep heat from being lost to the surroundings. We have a lid on top of this thing. And a thermometer inside measuring our solution. Okay, so the reaction itself is your system. The solution is what we're measuring, and the solution is your surroundings. So the heat that's lost by the reaction, it's lost because the temperature goes up, is gained by the surroundings. The surroundings increased in temperature, therefore the reaction lost that heat. It generated so much heat that it was exothermic and lost heat to the surroundings. Again, we cannot directly measure Q of reaction. But we can measure Q of solution. And Q of solution equals mass of solution times specific heat of solution times change in temperature of solution. So please pause because I need to erase to find lots of space of things. So we've got negative Q of reaction equals positive Q of solution. I know Q of solution is equal to the mass of the solution times specific heat of solution times change in temperature of solution. Q of solution, I've got 100 grams of solution. How do I know? Assume that the combined solution has a mass of 100 grams. Specific heat, 4.184 joules per gram degree C. And temperature, final temperature, 23.40 degrees C. Initial temperature, 22.60 degrees C. The difference here is 0.80 degrees C, so that does have two sig figs. That 0 here, the second 0 is significant. Q of solution, 334.4 joules. But I'm going to underline that second 3 because that's my sig figs. That means my Q of reaction is negative 334.4 joules. So important. Delta H for reaction is for the specified number of moles of reaction, of reactants, I apologize. So delta H for reaction is for the specified number of moles of reactants. The question wants delta H in kilojoules per mole of silver chloride. We need moles of silver chloride. Move that up here, find some space again. We know that we have 0.00500 moles silver nitrate or silver ion, whatever you want to say. We know that 1 mole of silver chloride is produced for every 1 mole of silver nitrate. Therefore, we have 0.00500 moles of silver chloride. We could do the same thing to make sure that the HCl is not limiting. 0.00500 moles of HCl. 1 mole of silver chloride to 1 mole of HCl. 0.00500 moles of silver chloride. So yes, we are going to prepare 0.005 moles of silver chloride. Neither reactant is limiting. Or in excess. They're just equal. They're what we call equal molar. But that means I can calculate my kilojoules per mole. Delta H of reaction is Q of reaction divided by the number of moles of silver chloride, negative 334.4 joules, divided by 0.00500 moles silver chloride, gives me negative 67,000 joules per mole silver chloride, or negative 67 kilojoules per mole of silver chloride. I know this problem is complex. It takes time thinking about what the system is, what the surroundings are, and really wrapping your brain around those two concepts and keeping them straight. I recommend taking your time, working problems, looking at the additional practice, etc., to really get comfortable with these problems. But it's not too bad if you can recognize your system and surroundings. The hardest part is getting those down. Once you get that down, the rest should come more easily.